Hello everybody! I hope everyone's having a wonderful day. So today we're going to be proving another fun example for big O. So we're going to prove the following claim, then I'm going to give you an example of what I mean by this statement. So I'm going to consider for all integers k, they're all going to be non-negative, and I'm going to consider positive real value called epsilon. So these are going to be both fixed, as in they're constants, and I'm going to prove to you that n to the power of k is big O of n to the power of k plus epsilon. So just as to give you an example of what this means. So imagine if I gave you, for example, if k was equal to 2, if I gave you n squared is big O of n to the 2 plus, say, 0.01, and say epsilon is equal to 0.01. So this would be n to the power of 2.01. This example will show you how you can tackle claims of this nature. So anyways, what we're going to do is we're going to exploit the fact that we know functions that look like this are in fact increasing functions. So we're going to use that in our proof. So that's going to be something I'm just going to take as a given. So what do we do normally when I prove claims like this? I say what I'm going to do. So let's do that. So we find constants. We find constants. C, remember C is a positive real number. And n0. N0 is what? It is a positive integer, right? So that for all n greater or equal to n0, it's that n to the power of k is less than or equal to c times n to the power of k plus epsilon. Now what we're going to do is I'm going to divide both sides of this inequality by what? The lower of these two terms. Which one is the smaller of these two polynomial-esque terms here? It's this one, right? Because that one's going to be strictly bigger than 0, meaning that it's going to end up being something like slightly larger when I add these two. So for all n greater or equal to 1, now it's very important when I write down these things like for all n greater or equal to 1, I'm invoking a domain for which this statement is going to be true. It's important that we quantify what our statements mean so that we can derive n0 later. So for all n greater or equal to 1, observe that when we divide both sides of the inequality by n to the power of k, then we get n to the power of k over n to the power of k is less than or equal to c times n to the power of k plus epsilon over n to the power of k, which this is in fact equal to c times n to the power of epsilon, which this, if you rewrite this out, this is true if and only if c times n to the power of epsilon is in fact greater or equal to 1. So what am I going to do now? So I'm going to pick C. Now I'm going to invoke some property I have of that inequality over there. Pick C is equal to 1. And the reason why I pick 1 is that it makes it a little easier to play around with. So then I just have n to the power of epsilon is greater or equal to 1. As long as I can invoke something about a polynomial of that form, we're okay. Then, so pick C is equal to 1. Then we need to find n0 such that n to the power of epsilon is greater or equal to 1 for all n greater or equal to n0. Well, this is nice and easy, right? Observe that n to the power of epsilon is greater or equal to 1 for all n greater or equal to 1. So we can select n0 is equal to 1. Now, before I get a little too ahead of myself, if this step went a little too fast for you, let me break it down in simpler terms, okay? So first, you would agree with me that if epsilon was equal to 1, that this would indeed be true for all n greater or equal to 1, right? If epsilon was, say, bigger than 1, you would agree with me that this statement was rather straightforward, right? Okay, the natural question is, okay, well, what do we know about this right here? Well, this right here is in fact an increasing function. This is increasing. Now, what exactly is 1 to the power of epsilon? Well, what's 1 to any power? What is 1 to some exponent? It's 1, right? So it's an increasing function, and when I put in 1 to the epsilon, it's equal to 1. Hence, it must be that this inequality holds for all n greater or equal to 1. It's those two facts that make this work. So we can select n0 is equal to 1. Therefore, by the definition of big O, n to the power of k is big O of n to the power of k plus epsilon. So like I said before, you can use this to prove all sorts of fun claims like n squared is, whoops, I forgot to finish the proof. There we go. Things like this, n to the 2.1, like 2.01 right there. You can prove all sorts of claims like this using that. And keep in mind that epsilon can be as big as you want it to be as long as it's some finite constant. So you can see that this is actually a pretty broad statement in regard, and this gives you the simple recipe for how to deal with that. So all I did was I invoked the fact that this polynomial here for this fixed epsilon is in fact an increasing function, and I know what its value is when n is equal to 1, right? It's 1. That doesn't matter what epsilon is. It's just going to be 1. And it's increasing, so it's never going to be less than 1. Okay? So that's all I'm going to be doing here, and that should crack things up with this example. Wasn't that nice and easy? We just did that little trick there. So that being said, I want to say thank you very much, and have yourself a beautiful day. I'll see you later.